each year, the other one being the Pi Day colloquium in the spring. That one's more about math as fun and entertainment. And this one is in honor of our dear and beloved departed mathematician Mike Skaff, who, aside from working here and giving great quality math instruction for about 40 years, he also did a lot of work out in industry. And so this is dedicated to, in his name, it's a math talk about the use of mathematics in industry or business or some area where you might not expect it. Now, before I introduce today's speaker, who you all know, and he doesn't really need an introduction, I want to talk about statistics. I teach a statistics class now and then, and one of the first projects I always give out in this class is entitled Why Mathematicians Seldom Gamble. Now, the chuckles you might hear around you are due to the fact that Mike Skaff himself wrote a book on a winning system for playing craps. I'm a pretty good poker player. Rumor has it Katie's even better. And our speaker today is an ex-professional blackjack player. And he's going to be talking today about the mathematics behind a betting system used in blackjack and why it's actually not as good as people say it is. Our Michael Canjar.
Well, thank you very much. And I consider it a great honor to be here to give the Skaff Memorial Lecture. As I said at last year's lecture, Dr. Skaff was probably the primary reason I became a mathematician, so students can blame me for all their suffering now. But when I was a freshman, I wasn't sure what I was going to major in, and I was my father's dean of engineering. He was my advisor. He said, "We always take math for your electives because you can never have too much math." And he didn't go into your, but I thought I'd be in physics or engineering, but when I took math 435, real analysis, that was really the first course that really excited me. And that's Dr. Skaff's course. I took 3 of his as an undergraduate. And I'm also very delighted to have 2 of his close relatives here. His beloved wife, Carolyn, is there, along with his firstborn son, Michael. And I'm glad that both of you could come and hear this. You can see that I say just a personal comment about myself. Not now, Prasad. You can come in, but this part's important. Many of you know that I have cancer, and those of you who are in object-oriented programming know that in design, we like to design our objects with destructors so that they make sure they don't leave a mess behind. So I've arranged for the orderly transfer of my assets by setting up a living trust, including my intellectual property. And I've set up a sub-trust for intellectual property. And I've basically, any of my class notes, any of my books, anything my trustee is authorized to share with faculty or students is appropriate. If anybody wants to sell anything, turn it into a book, then my royalties will be donated to some memorial funds that I've designated. And if there are to be any royalties generated, if you decide to sell the tape, then I've left instructions that those should be donated to the Skaff Memorial Fund, which is a scholarship we do. And my intellectual property trustee is my longtime colleague and very good friend, Dr. Catherine E. Snyder. So after I'm gone, if you want any of my class notes or anything, she will own it all. And now you can take her out, Prasad, and whatever you need to do.
I know.
Okay, now we're going to get into the main subject of our talk, entitled "Why Optimal Betting is Not Optimal," and I guess nobody is laughing. So the first joke has failed miserably, and this is not a good sign. But anyways, there is going to be a certain amount of self-promotion in here, partly because I'm basically a ham, and when I'm on camera, I can't resist. But also, something you students need to know, and especially you junior faculty, you do need to learn how to promote yourselves. It is something you're going to have to do. It's not enough to know something. You do have to know how to promote it. And you're certainly going to see a textbook example of self-promotion. Now, I'm going to talk about, what I'm talking about is not gambling, but advantage play. An advantage player is somebody who engages in positive expectation games with the intent of making a profit. Such as casinos make positive expectation gambles. Insurance companies, you probably don't think of gamblers, but you probably think of professional gamblers. I call semi-professional people who have a day job and are not a whole income like myself. I'll use the term AP, advantage player, for the latter. APs resent the term gamblers because they think of gamblers as somebody who goes to the casino for fun. And what APs do is not fun, it's actually work. Now, in case you're wondering what casino games can give you positive expectation, I leave poker out because that's a different thing. Certainly blackjack with card counting. Certainly video poker, that's much more difficult to do. Sports betting. My betting theory is going to apply to all of these. Occasionally there's special promotions that a casino has, a special rule that gives a positive expectation. Sometimes there's even a mistake. There's a high-profile case of a casino in Mississippi that had a dice game. They had a pay table where they had a typo on it, and it was a positive expectation. A local guy made a fortune until he let the news leak out, and then every professional gambler in the country descended on it, and that ended it. Blackjack is uniquely suited to computer analysis. The math is straightforward, 427 level, but the computations require it. We really didn't understand blackjack until the computer era. I will tell you a little bit of my own AP career from 29 to 11. I've recently retired. I made a little over $250,000. That was about 3,300 hours. Curiously, I made most of that in that 6-year window. In fact, I made all of it in that 6-year window. My last all-time high was on December 17th when my net win was 285. I then, in the next 6 months, had a $70,000 downturn. You do lose money if you're a professional gambler, even if you have the edge. And by the way, that's not as bad as the stock market. So if you think this is really gambling, the stock market's worse. I did have some reduction. I lost money at the beginning of my career, and I didn't make back this. I came within one card of making this back. 2002 was my big break. I made $45,000. I went over the 100,000 mark in 2004 and the 200,000 in 2006. You probably can't do this today because conditions are bad, but I probably only started with a bankroll of about $10,000. And growing your bankroll and bet sizing is really what this is about. I'm not going to teach you how to play blackjack or to play video poker, but if you have skill in that and you want to know, I have a bankroll, how do I make it grow? That's what this is going to be all about. I'm going to assume that the results of the game are a random variable. There are outcomes. For example, one outcome is we may win, the next one would be +1. We may lose our bet, -2. We may win double, that's +3 of the probabilities. In probability theory, there are moments. If you've not heard about them, you'll still be able to catch most of the talk. The first moment is your average, sometimes called your expectation. Your variance is the second moment minus mu squared. And in gambling, your expectations are very small, like 1 or 2%. So variance and second moment are almost the same. Variance is, the square root of variance is called sigma for standard deviation. That's a measure of risk or volatility. If you haven't had statistics, sigma is really going to be our measure of risk and volatility. And we're only looking at positive expectation games throughout this time. We're not interested in losing money in a slot machine. We're interested when we have a positive expectation. The simplest kind of thing you can have is a bet. You're going to bet that Canjar is going to finish on time. If you win, you get 100% of your money back. If you lose 100%. I'll call that a coin tossing game. It's really a biased coin to have positive expectation. And I won't assume that the coin can't land on its side, that there's no ties. I use little b for your bet size, capital B for that. Expected value will be $1. Your expectation may be 1%, like 1%, 2%. B is your bet size, so you have a 2% advantage on a $100 bet. Your expected value would be $2. Okay, now the first thing you might think about doing if you're going to go to a casino is you say, how am I going to bet my money? What's my goal? You might say make the most money, get the most expected value. I'm going to call that criterion A. Let's say you have a coin tossing game, and this came up, this came up too fast. Your expected value would be your mean times your bet size. And I'd probably give it away. This is a constant. This is your game, 2%, 1%, 5%. You can control your bet size. How would you make that as big as possible? In your function, make it as big as possible. There's no maximum. If I say 1% of your bet size, you make the most money by having the biggest possible bet. So you would bet your entire bankroll. If you lose, you're ruined. If you win, you'd bet your entire bankroll again. After 2 rounds, your probability of winning is p squared, and you would have quadrupled your bank. And that pattern continues. Now, of course, you'll see I put the general form as I show what happened if you had an unrealistically huge 10% edge. After 10 flips, you'd have a 99.7% chance of losing. You wouldn't have any money left. But boy, when you did have money, you'd be at $512. Your expectation here is going to infinity. Your probability of losing is approaching 100%. Your expectation is going to infinity. So maximizing EV gives you almost certain ruin, even though it gives you infinite expectation. By the way, this is sort of a discontinuity of the expectation operator. And this is theoretical. This says 5 times 10 to the 8th. What's 5 times 10 to the 8th? Is that 50 or 500 million? You're probably not going to find a casino that's going to allow you to bet 5 blocks. They want to bet 500 million. So this is a mathematical model. So now we're going to come to the classical gambler's ruin problem. And
Mike, how many tries do you get before you get to that 500 million?
30. 30.
Oh, 30.
Let me check one thing here. Okay. Okay. And so here we have the problem: if we bet as big as we want to maximize our expectation, we get ruined. 100% certainty of getting ruined in the limit. So we're going to now discuss what's called the gambler's ruin problem, which is a classic problem in mathematics. We're going to go a specific game, and we'll fix it, and we know the mean, and we know the standard deviation. And I'm going to fix my bet size permanently. I'm going to say I'm going to bet $100 or $200. And these parameters are fixed. When I win, I'm going to reinvest them in my bank. When I lose, my bank goes down. There's a possibility I may have enough loss that my bank falls to 0 and I'm what we call ruined. Let R of B be the probability that I'm ruined. Okay? It's from bank B. So that's going to depend. If I start with a 10K bank, 1 probability. If I start with 20K in my bank, it'll be a lower probability. So this is a function that says, given a bankroll B and playing this game with a certain bet, what's the probability of ruin? We call that the risk of ruin. Oh, you're in the wrong page. The title page is out. So I wonder if we can edit the video in the range. That probably not. Here's some obvious properties of the ruin function. There are probabilities, and I'm only interested in positive numbers. These are bankrolls, so the domain of this is positive numbers. Property of independence says that the probability of ruining R of B1 plus B2 is the product. In other words, if you have 30,000 in your bank, you first ruin, you can think of that as I first ruin 10,000 and then ruin a $20,000 bank. So that's a simple thing. Does anybody, preferably students, know any function with that property? That e to the x plus y, that r of x plus y, what? Any function with that property? I sort of give it away. We talked about this in calculus. I see some of my calculus students are. Exponential function has that property. E to the minus x is that way. I'd have to have e to the minus x for that. E to any constant times that. It's clear that an exponential function has this property. It takes a little more work to show that any function with this property is an exponential function, but it is. So your ruin function, it is a theorem you can prove, and this is an exercise, but it is hard. I'll give you some hints if you want to tackle it. There's a constant for which that comes up. By the way this constant is chosen, if you have a positive expectation gain, the constant is greater than 0. Once you know there's a constant like that, you can do some straightforward work to figure out some properties of it and define it. That's what my ruin function is. It satisfies this equation. Remember, x's are my payoffs. If you have a game where you can win 2 to 1 or 3 to 1 or 4 to 1, those x's take on those different values. P's are those probabilities. This is a characteristic function. Alpha equals 0 is a trivial solution, but it has a unique non-trivial solution. And that solution of that equation is what you get alpha. By the way, in classical mathematics, they wrote that as lambda to the b. You notice e to the alpha to the b. E to the minus alpha b and lambda b are equivalent. Well, of course, the change would be alpha to the minus log. The little pre-calculus problem here. This is a polynomial if you have rational payoffs, which it is, and classical mathematicians were fascinated with that polynomial. But I think it's a better way to write it here, one of which is to convert monetary units. Your bank is either dollars or, what do you call your Canadian dollars? Whatever they are. Valuable, maybe you call them. It could be Canadian dollars, it could be rubles, it could be euros. You're going to have different alphas. It's just a simple factor. Converting this is a pain. But more important, it becomes very easy to derive the Canjar E-theory equation, which I'm going to put on the board next. It expresses the characteristic function in terms of the moments, M1, M2, M3, M4. And once you think of the Ruin function this way, it's not hard. This is just a Taylor series. You can do it with 142 if you know what moments are. You just have to realize that. These are the two papers where the equation is. Professor Ethier from Utah and I came up with this equation independently. Yeah. I'm sorry?
I'm sorry to interrupt, but those of you who haven't read that paper you just mentioned of Professor Canjar.
The paper I asked you to look at was the different paper.
Wasn't it this one? Oh, I'm
No,
sorry.
no, that's a different paper.
I'm sorry.
It's a different paper. So that I quoted two of my papers in here. So yeah, I appreciate what you were going to say, but it's okay. Okay. These alphas are like 1% or 2%, so these alpha cubes and alpha 4s are small. If the skew term, M3 is related to skew, is relatively small, such as sports betting or blackjack, then you can make this approximation. And your Ruin parameters, your mean over your variance. Everything should be expressed in terms of mean and variance, in terms of what you expect to make, whether you've got a 1% or 2% hedge, and what your risk is. Now, actual gamblers knew that this equation was here. We had some intuitive arguments for it. You could see it from Monte Carlo things. But we also knew that it broke down. We realized it broke down for high skew. But there was no real formal explanation of how those are related. And that's the beauty of this equation. And that's one of the things those papers deal with, is how it breaks down. By the way, this equation here is exact for a coin tossing game. That's a classical result. Even though it's an approximation, it overstates your risk of ruin. So if you calculate your risk of ruin as 7%, you'll know that your risk of ruin is less than or equal to 7%, which I think is desirable. Here's an application. I know Professor Damien's going to ask me, what is this stuff good for? So here's the type of thing we do. Suppose I know I have a 2% edge, and let me make life easy and assume my standard deviation is 1. In blackjack, it's definitely not 1. Sports betting, it's not exactly 1. My gambler starts with a $10,000 bank. They want to keep their risk of ruin under 5%. They're going to bet as much as they can, but they only want to tolerate a 5% chance of going bust. So do you understand the issue? The bigger they bet, the more chance they have of going bust. So they decided they'll accept a 1/20. Well, it's a simple algebra exercise to solve it. I've done it. By the way, when you see an equation like this, always ask yourself if these parameters, I'm talking mostly to students because I hope the faculty know this. I think they do. Always ask yourself, do the parameters make sense? This says that the bankroll you need is proportional to your variance. The more volatile your game, the more risk, the bigger bank you need. If you have a game with a high volatility, it needs that. The bigger edge you have, whether you have a 2% or 3% edge, the smaller. R is a number less than 1. R is a probability. It's a negative. Minus log is positive. And that says that if you don't want much risk, the smaller R is, the more demanding you are on risk, the bigger bank you need. So they do make sense. Once you have that, you can just substitute your numbers in. I did it. For the 5% risk of ruin, it came out to be about 75. My bank has to be 75 bets. My bank's $10,000, so I divide by 75 and realize I can bet $133 on this game and have a 5% risk of ruin. If I wanted a 1% risk of ruin, I have to bet smaller, and I would be down to $87. Any questions on what we've done here? Now,
That's my.
what?
How do you know mu? How do you
Oh,
know
well, you measure that. Like if it's a blackjack game, you do a computer analysis or a computer simulation. If it's a dice game, you compute the odds combinatorially. But you have to do the analysis for your game. So that's a good point. So we do the analysis, and in blackjack we do simulations, Monte Carlos, or we do combinatorial analysis. There's a whole different topic on computing it for different games, but that's what mathematicians can do. Good question. Now, 5% risk. Now, so with $10,000 bank, you can only bet $133. 5% doesn't seem like much, but think about this. I think we have more than 20 people here. We have more than 20 people. Make sure it's clear on the tape. We have hundreds of people, but clearly more than 20. That means if you all went out with a $10,000 bank and you had this game available, one of you would go bust. One of you would lose $10,000, even playing with an edge. Now, that may or may not be acceptable, and it's not acceptable if you lose a light. One thing to realize is that some of you will start winning, and maybe your bank's now 30 or 40,000. From that point on, your risk of ruin has gone down. On the other hand, if you lose, your risk of ruin goes up. So, for example, if you double your starting bank, it's an exponential function, so your risk of ruin would be, if you started with 5% and doubled your bank, you would now have a 0.25% chance of ruining, which makes you feel better. If you lost half your bank, you would have the 1/2 power of this, and you'd have 11%. Now, what a lot of people might do, since 5% isn't very, it still can happen, is that if you win money, you say, well, my risk of ruin is so small, I can now bet more. And obviously that happened to me. I mean, I didn't make the money I did just betting with a $10,000 bank. Or if you lose money, you resize down. By the way, if you do that, your lifetime risk of ruin would be more than 5% if you adopt that as a strategy. Now you could do this. This gives the subject of resizing. That is, as the bankroll grows, you decide to raise your betting levels and bet more. The same game, you're now going to bet more money. Now, mathematically, we could talk about continuous resizing, that after every bet you resize. Now you may think that's not realistic, but if you know how compound interest works at a bank, you put money into a bank and there's compound interest, they can always give you an effective annual yield. Well, whatever strategy you have for resizing, you can always come up with a continuous equivalent. So it's nice to analyze the game mathematically. And this gives us our segue to the whole topic of proportional betting. I prepared a lot of slides on proportional betting because it's an interesting subject, but I realized I just wasn't going to have time to get it today. So I've left them there on your handout, and I left them here as an appendix. But what I'm going to do is just summarize the key features that are needed for the main thread of my talk. The idea is you start with your bank, and you're going to bet a fraction of it, like 2% or 5% or 12%. That means that your capital will grow exponentially. If you think about it, it's like in reinvesting in compound interest. It could decay exponentially as well. It will be the case that since your bankroll is an exponential function, its logarithm will just be an ordinary function, a linear function. Now that means the logarithm will have the so-called normal distribution, the bell-shaped curve. I hope if you've had 427, you know what a bell-shaped curve is. If you don't, it won't be the main point for what we have to say here. The mean of your bankroll is always going to go up if you have positive expectation. We looked at the extreme example of betting 100% of your bank a while back. Remember when we bet 100% of our bank, we knew we were going to go bust. But we knew that our expectation was as big as possible. Your expected bank, the mean is the expectation, is increasing. But the median, so bigger F's give bigger means, but your median of your bank may go down. And in fact, all the percentiles may go down. Your 90th percentile level may go down. So you may be in a situation where you're almost certain to lose, but the small times that you win, you make such a big fortune, you have positive expectation. Okay, we talk about the exponential growth rate is the expected log of your bank. And this is sort of, it's an exponential function, so it's an e to the RT. That's basically what the R is. This is also going to be the median, not of the bank, but of the logarithm of the bank. Now, there's an important method of gambling which is often called optimal gambling, and that's why I said this is why optimal betting is not optimal. And that's named after a person named Kelly, and it's called the Kelly criterion. The criterion is size your bets, which means come up with the fraction that gives you the maximum value of the expected growth rate. Calculus, you probably studied making maximum and minimum functions. Here's an application, make this as big as possible. By the way, this is what a law normal distribution looks like. There's a nice little Wikipedia article on it. I have a link there. And these are just summarizing what I had on the previous slide. Okay, here's a criterion. I'm going to call this criterion B. You remember criterion A was just make the most amount of money we can by having the biggest expectation. Criterion B is maximizing your exponential growth rate, which basically is going to maximize the median of your bankroll. And there's even a Wikipedia article on that. Kelly, so that is our criterion, and I'm going to give you some equations soon which are going to do this. I'll give you some history. Kelly generalized some work of Claude Shannon. I don't know if some of you recognize the name Claude Shannon. He was a big name in mathematics. They both worked at Bell Labs, and Claude Shannon did a lot of work in information theory. One thing that he did was study communication over a noisy channel, where I send a signal and you may or may not get it. I send you a 1, but you might read it as a 0. I send you a 0 and you might read it as a 1. Now, then he looked at the probabilities of a 1 or a 0 as a measure of the noise, and he came up with equations. And then Kelly came up with sort of a gambling analogy of that, and that developed the Kelly criterion. If you read the appendix, I went through some of the equations in a coin tossing game. And you could go through and do this derivation and come up with this. I think this is a little aside which I'm making, come up with this equation. Kelly, in his paper, gave this form. And I've seen this quoted uncritically in various literature, such as Epstein's book on gambling theory is a classic work. Now I saw this and I said, well, I can get this high school exercise to get this. But I couldn't figure out. By the way, a good mathematician, if you read an article and there's an equation, try to derive it yourself, because that's how you're going to know that you understand it. It took me a long time to figure out why I came up with this equation. And Kelly said this Shannon equation, which was a big equation in Shannon's work, was this. Anybody see how those two equations can be equal? Any of the students? Any of the faculty? We didn't discuss this ahead of time, did we? No. Yeah, Shannon was working in base 2 logarithms. He was working in communication theory, sending 1s and 0s. In computer science, I mentioned we often use base 2 logs. I mentioned in calculus you can use other bases, including base 2 logs. So but Shannon's paper is very clear. I dug it up and it said all our logarithms are base 2. But a lot of times people quote this by mentioning their base 2 logarithms. If you have a game where the skew is modest, there's a moment equation, just like for the Canjar E-theory equation. There's a moment equation in terms of mean, standard deviation, skew, etc. But if you neglect, for most games, you can just look at the first 2 terms. Remember, the Kelly criterion is to come up with F, your betting fraction. It's a nice little quadratic. It's a simple calculus problem to find the maximum of that, but it's really a high school algebra problem because it's a parabola, and the maximum occurs at the vertex. It's symmetric about the vertex. Mean over standard deviation is your betting fraction. Again, the more volatile your game, the smaller you have to bet. The bigger edge you have, the bigger you bet. The interesting thing about this is it's a quadratic. If the fraction's big enough, it's negative. We saw the extreme case where if your fraction's 100%, you're certain to go bust. If the fraction's big enough, you're in negative territory. And if to the extent this quadratic model applies, and it applies very well in sports betting and in blackjack, in games like that don't have skew, it's about twice your optimal level. Oh, by the way, this equation here is exact in the moment form for coin tossing. You can actually, coin tossing has only 2 outcomes. It's very easy to come up with exact equations. Oh, people will call this the Kelly bet. So if you hear somebody say, what's the Kelly bet for that? It's the fraction of your bankroll that's mean over standard deviation. Now, Ed Thorpe invented card counting. He's credited with it. He really invented the computer analysis. There were some individual blackjack players in the 50s who had learned by empirically discovered that there were counting systems that might work. They were poor systems because they didn't have analysis. But just when computers were coming to universities, Thorpe was a math professor at MIT, and he wrote the first book on card counting. He analyzed it, proved that you could have a card counting system that worked. Once he knew that he had card counting, he wanted to say, how am I going to bet optimally in this game? I can go to the casino and get a 2% edge. What do I bet? Do I bet my whole bank and go bankrupt? Do I bet a small amount? And so he picked up Kelly's paper. And he proved two important things about this Kelly betting system. This system that says bet a fraction of your bankroll each time, the fraction being mean over expectation over volatility, by that mu over sigma. If we take any other betting system, and I'll come back to the quotes, it's going to win. Kelly's going to win more. Kelly's going to win so much more that if you want Kelly to win 100 times more, in enough time, Kelly will win 100 times more. You want to win 1,000 times more, enough time to win 1,000 times more. If you say, I want to reach $1 million, it'd be nice reaching $1 million, Kelly will get there faster than any other betting system. So it has many properties that are optimal. For that reason, Kelly is often called the optimal betting in the sense that it does beat any other essentially different strategy. The reason for those weasel words, essentially different strategy, is to rule out a tournament situation. Let's say you and I are in a tournament and we're going to bet money. It's funny money because it's a play money, it's a tournament, but there'll be a prize for comes in first. They do have that. And the person who has the most money at the end wins. If I know your betting system, I have a big advantage that I can beat you. Because if I know what you're going to bet before you bet, I can mimic your bets. And in a tournament, that's a very powerful thing. So you have to rule out somebody knowing the Kelly system and jiggling it a little bit in a tournament situation. And that's basically why you have the weasel words there. It's called optimal betting, but advanced players don't use Kelly betting. Very few of us do. I never use Kelly betting. That's an interesting question. Why? Very bright people. You have to be a bright person to be an advanced player. Trust me on that. Who know a little bit about mathematics, or at least appreciate mathematics. Know if the computer says you've got a 2% edge, they know what that means. Why don't they use this optimal betting? It has very big fluctuations. If y'all go on and play Kelly, 50% of you at some time will lose half your bank. If you have $100,000 banks, you'll lose 50,000. I mentioned I lost 70,000. That's not very pleasant. There's a 10% chance you'll lose 90% of your bank. Again, if you have a $100,000 bank, you'll lose 90,000. With Kelly, that's a 1 out of 10 chance. If there's 20 people here, 2 of you would lose it. And this is for any number. There's a 17% chance that your bank will fold a 17% of it. I use that as a generic constant. Kelly raises what's called the long run index by 4. For any game, you can measure how fast it gets to the long run. And typically blackjack, it might be 200 hours, and maybe 800 with Kelly. And I'm going to give you a table. I put the table on the very back. Many players use a fractional Kelly system, such as take the Kelly bet and bet half of it. Take the Kelly bet and bet a third of it. It does reduce the fluctuations. Here's a table that shows what happens to Kelly. This is a dimensionless parameter that gives your volume of play, adjusting for the game quality. It's based on this parameter, mean over standard, volatility over advantage squared. And it's used as a long run index. 100% is where we start. So any number less than 100% is losing. And this is the probability distribution. Now, I use 200 hours, which is probably reasonable for blackjack games. They could be all over the place, depending on game quality. And to come back to Prasad's question, yeah, if you gave me a game with rules and dealing policy, we would run an analysis and say, okay, our mean is this, our standard deviation is this is what our no is. 16 no's, 3,200 hours is about my career. 2.3% are to the left of this. 97% are to the left of it, meaning 2.3% are to the right. The table is symmetric. So after 3,200 hours, over 2% of the people would still be in the hole. So imagine, let's back up here. After 800 hours, 2% of the people would be, well, 16% of the people would be behind even after 800 hours of playing an advantage. 14%, a small amount, 2% would only have 14% of their bank. They would have started with $100,000 and only have 14,000. Now, 2% may not seem like a lot, but again, you had a room with 50 people, 2 would be there, and he'll say, what happened to me? And you say, well, some poor schlock has to be at the far end of the bell curve because there's 2% there, and you just drew the unlucky card. So and these are apparently unacceptable swings, which segues us to utility theory, which is the main topic of my talk. And it's here where we're going to get in touch with our own feelings. I want to start with a classical mathematical problem called the St. Petersburg paradox. I'm going to flip a coin, and let's say that Katie, Dr. Snyder here, plays, and I'm going to pay her a payoff. It's going to be based on when a head comes up. If t is the number of tails before we get a head, I'll pay 2 to the t. So if it's t, tail, 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 head, 3 tails and then a head, I'll pay $8. Or if Dr. Prasad wants to play, or any of you want to play, we'll play this game. If 6 tails come up, you'd get $64. If there were 30 tails, if there were 20 tails and a head, I would have to pay you $1 million. Now, if you're worried that I have the assets, I got to deal with Gates or Warren Buffett. They'll come in and bank together. So assume that we can cover. How much would, now, I'm not giving this money away. You have to pay an entry fee. Okay, this is not charity. How much would you pay? Who would pay me $50,000 to play this game? Who would pay me?
You mean we have an infinite lifetime to play it in?
Actually, 50 flips is going to be pretty good. 50 flips, you own the one. Anybody going to pay $10,000? How about $100? Do you know what the expectation of this game is? Let's compute the expectation. If I have t tails, I pay off 2 to the t, and the probability is 1 over t to the half. So on that outcome, I make a half. So you make a $half, just you get if there are no tails, you get a $half. Tail head, you make, well, let's go down here. You have a 1/16th chance of making $8. 1/16th chance of making $8 is an expectation of $0.50. You have a 1 over 256 chance of making $128. Again, and you make half a buck. But there's infinitely many of those. So if you add them up, you have infinite expectation. There's a game with infinite expectation, and you can't find people who give you $100 to play this game. That's a sort of a sociological fact, which I think we've demonstrated here. We have a room of math professors, and we have a room of very talented udmercy students, the best in Michigan, best in the country, really. Get that on the tape, too, by the way. And none of you would even bid $500 for this. So this is the paradox. It's not a mathematical paradox. It's sort of a sociological paradox. We want to get in touch with your feelings on why you wouldn't pay $100. This is going to give me my segue to certainty equivalent and utility theory. In a game like this, whatever you would pay, $4 or $8 or $10, we'll call that the certainty equivalent of that game. How much you have a gamble, how much certain money is that worth? Let's say I give you a gamble where I say I'll give you 10% chance of making $1,000 bucks. That's $100 expectation, but you might not pay me $100 for a one, I get $100 and 10% time to get back. So there's something called certainty equivalent. It's a subjective measure, but there are common sense rules, and they lead to a utility function. Utility basically is a function of your wealth. It's going to be a mathematical function that says how valuable wealth is. The concept is that where utility theory becomes interesting is we think there's diminishing returns. If you made $1 million tomorrow, your life would be a lot better. Would it be twice as good if you made $2 million? Most people would say no. My first $1 million is a lot more valuable to me than my second. If I had $1 million, I wouldn't bet 50-50 to get $2 million. I wouldn't bet my million on 50% chance to get $2 million. That means So that's why we have utility function. In some respect, how valuable. You can think of it as how much use you can make of the utility theory. We assume that the more wealth you have, the better. So all my utilities are going to be increasing functions and have positive derivative. I'm going to assume we all have derivatives. Most people, we just said it's concave down, fall into this category. Now I'm going to give you some examples of utility functions, and this may seem like a strange definition of equivalent, and I'll come back to why this is equivalent, but two functions are the same utility if there's a linear transformation, and since they all got to be increasing, I've got to keep that constant positive. Saying money's worth what it's worth. If you do make 2 million, it's worth twice as much as 1 million. That's a linear function. Well, that is a utility. It doesn't have, it has 0 second derivative. Log function, that's concave down and increasing. Power functions that look like this, these are concave down and increasing, and I'm going to have positive numbers in there. Or an exponential function like that, 1 minus exp, 1 minus e to the w. The reason for the funky colors is I've graphed them, and the colors on the graph are what they are here. So that's why I'm putting different colors. The reason for these constants is I normalized all of these. I can define anything as my baseline as my 0, because we measure the difference in utility. So I'm going to take our current wealth, 1 times our current wealth is 0, and I've fudged the constants so these all have the same slope. Otherwise, I could really distort the picture by, I could throw in a constant and make the slope look terrible. 1 and 2 are unbounded. 3 and 4 are bounded. That's a point we'll come back to. And I graphed the power with p equals 1, but they're similar. Now, there are some simple rules. How do we find what certainty equivalent is? We talk about our expected utility. That's our average utility. A certainty equivalent of a wager is how much certain money would be added to our wealth, which would give us the same certainty equivalent. Now this is an implicit equation, and I usually work with it, but you can solve this equation explicitly with U inverse, and if you'd like an explicit formula, you can. And we know that our utilities have inverses because, I realize it's late in the talk, but there's one assumption I made about utilities which guarantees they have inverse functions. Upper level math students, and I hope the math professors see this. Now, Dr. Dasgupta reviewed the notes, so it's probably, but you probably knew it before. Remember, my functions are increasing, so they have positive derivative. Okay, two utilities are equivalent if they generate the same certainty equivalence, or this condition I gave before. And these two mean the same thing. 1 to 2 is easy, 2 to 1 is trickier. I'm going a little fast because I'm trying to cut to the chase because I know I'm starting to run short of time. Now, there's a quadratic approximation to utility theory, to certainty equivalent. It's not as easy as it looks because I had that complex inverse equation or implicit equation. But your certainty equivalent is your expectation times your bank minus sigma squared b squared. And here, these are dollar figures. This is your bet size. So K is a constant which represents your risk tolerance or your risk aversion. I made it 2 times K instead of just K in the bottom because this has a significance, and I'll explain why it's called the Kelly equivalent bank. But given your utility functions, you can compute them this way. And if you want to see a derivation of this, for this paper, the referees said, the editor said, we ought to have some comment because I use certainty equivalent a lot in the paper. And the referees said, why don't you give us an exposition, and I put that in that paper there. Now you can make your comment.
I'm sorry that interrupt again because the previous one wasn't there. This is the one I read, and I can tell you that it was my delight to read that. It's really a superb exposition of the things, and it brings in various kinds of things together, math and other things, and which are important in various ways. And I found, for example, a proof of the strong law of large numbers relating to some of the things that Dr. Canjar has explained. So, I would just recommend that as even if you are just starting at the paper.
This is another example of shameless self-promotion. I said I was going to give you lessons on it.
You know we set that one up.
Well, obviously it was set up. I mean, you gave it away. I mean, if you're going to do performance art, you got to get your lines on cue.
You get your money back from him because he messed it up.
But it was
You're
free.
supposed to say no.
But but this is a serious point. Get people who are knowledgeable in the field and respected to review your work, and then if they like it, say, well, you make some comments about it. Now, you should know that the faculty think of Dr. Dasgupta as our top theoretician, so he's the person that I got because I knew that that would cut a lot of weight with the faculty. The beautiful thing about this equation is it says you have some expectation, but it's not worth that. You have to make a subtraction for risk. And you can think of this as the cost is the cost of your risk. For example, if your EV is $100, but you say there's risk in this bet, and the risk is worth $40 for me, your certainty equivalent is $60. If you bet big enough, this will go negative, and you'll have negative certainty equivalent. You can have positive certainty equivalent for negative bets. For example, I have a bet with my insurance company that my house will burn down. If my house burns down, they pay me. That's a negative expectation bet. They're not giving me good odds. They have the odds in their favor, but it reduces my risk. So utility theory allows us to say, when is insurance a good bet? When is it a good idea to make negative expectation bets? Okay, this is a principle we have. Now, we had criterion A was maximizing EV. Criterion B is the Kelly criterion. Criterion C is going to be size your bets to maximize your certainty equivalent. And that's what I'm going to promote today. By the way, it's a simple high school. This is a quadratic. Vertex of the quadratic comes there, is K. Optimal bet is mean over standard deviation times this constant. For Kelly betting, that constant was the bank. So this is playing the, in Kelly betting, I said, you bet a fraction of your bank, and this is what the fraction is. That's why I call that the Kelly equivalent bank. A Kelly player would say, that's just what my bank is. So that's why I use that term. It's very simple to see at the optimal betting level, your certainty equivalent is 1/2 of your expectation. The variance cost is 1/2. I have a beautiful graph here that explains the whole thing. This graph only requires high school algebra. The blue line is the linear term. The red line is the quadratic term. If you think about it, there's no loss in generality in assuming that points to 2. And it's basic, just principles of quadratic. Certainty equivalence, the difference between these. And this is actually, it's the property of this graph that the cost, this is the cost, it's 1/2 of what the expectation is. Now I rushed through that because I wanted to do these calculations. Let's apply this criterion. For linear remember, that says our bet size is going to be this fraction, which is based on our gain parameter, times mu prime over u double prime. For linear utility, this is well, it doesn't work because u prime double prime is negative. It leads you to bet as big as possible. For linear utility, this says bet as big as possible. Do criterion A. For log utility, it gives us the Kelly bet. Kelly betting is criterion A betting, utility betting for the log utility. Probably not surprising, that was doing your mean logarithm. So C criterion generalizes Kelly betting. For the power utility, it comes out to be a fraction of the Kelly bet. Kelly bet over something. If P is 1, it's half Kelly. Remember I said a lot of gamblers use half Kelly or quarter Kelly? That comes out of this. Finally, for the exponential utility, your bet doesn't have anything to do with your bank. It's fixed. Just like in the first example I gave with risk of ruin. Risk of ruin betting, fixed betting comes out of utility theory with that particular constant. So all forms of betting are subsumed in the C criterion betting. I chose the criterion level so you would think of Canjar and think of that as the C criterion. Now I want to come to the bottom line. Let's get in touch with our feelings. Bernoulli invented the St. Petersburg utility theory to resolve the St. Petersburg paradox. You remember the St. Petersburg paradox was this game that none of you would pay me to play even though it had infinite expectation. Bernoulli said, why is that? People are maximizing something called utility. I realize I'm almost out of time, but I think I can get to the chase still. He invented utility theory to resolve that paradox. And he said they have concave down utility. He used log utility, and he showed that there was a resolution, and he came up with a millionaire would pay $11. So probably consistent with what we did. However, that doesn't resolve the paradox. Thorpe showed that for log utility, there's still a St. Petersburg paradox. You just change the payoffs. What I'm going to do for log utility is going to apply to any unbounded utility. In the St. Petersburg paradox, I paid you, I paid you I paid you one half, two half, four halves, eight halves. I paid you 4, but I called that 8 halves. I put 8 halves here. Because here what I'm going to do is pay you 2 to the 8th, 2 to the 16th, 2 to the 32nd. So if you got 4 tails, I would pay you 2 to the 16th. Real quick, people, what's 2 to the 16th? 64,000, right? Here I'm going to pay you that. And my expected utility still comes out 1 half plus 1 half plus 1 half plus 1 half. So I can still cook up a game like this, which has infinite expected utility with log utility or with any other unbounded utility. I suggest, just as none of you would give me the $50,000 to play the St. Petersburg paradox, you wouldn't give it to me to play this game. This is a game which maximizes log utility. Remember, log utility was Kelly betting, which we said was optimal. But none of you are going to use log utility in analyzing this game. You won't pay me all your net worth for that. You won't pay me for any unbounded utility. So my conclusion, and where we're in touch with our own feelings, is that none of our utilities are unbounded. They're all bounded. We can't imagine having, we can't imagine any gamble that we would pay an infinite amount of money to play. And that means we don't have unbounded utilities. That means the betting system, the so-called optimal betting system, which optimizes the unbound, that is not really a utility. And so I rested my case through utility theory. We've completed a walk and seen that Kelly's not really the best, and the time's come to end my talk. Because on this note, my case I rest. But speaking of poetry, since this is the Skaff Memorial Lecture, I wanted to conclude. My last slide is the sonnet I wrote about Dr. Skaff and what he did in my life. I went to the school in 1969, and in departments found many a gaff. I found many a gaff, but in math there was a professor just so fine, and the name we called him was Dr. Skaff. I returned to Detroit to be department chair and made a discovery that brought lots of fun of another thing that we both did share, the marathons that he did run. Tragedy struck that day in June when a fibrillation would stop his heart. Our lives were changed that afternoon, as from this world he would depart. The field of math he caused me to enter, and I miss him so much, my long-term mentor. Thank you for coming, thank you for paying attention, thank you for taping it. I'm sorry I'm